When the exponent is not a positive integer, what can we say about 1 plus x to the m when m is not a positive integer? That is, how can we expand an expression like 1 plus x to the minus 2/3 in order to find a nice compact answer to this question? First, we define the binomial coefficient m choose k for all real numbers m. Definition 4.14. Let m be any real number and let k be a non-negative integer. Then m choose 0 is equals to 1 and m choose k is equals to m times m minus 1 times m minus 2 and so on times m minus k plus 1 divided by k factorial if k is greater than 0. This definition expands the definition of binomial coefficients for positive integers. Let us consider the Taylor series of 1 plus x to the m around x equals to 0. Note that the nth derivative of 1 plus x to the m is n with sub-index n times 1 plus x to the m minus n. And this expression takes the value m with sub-index n equals to m factorial divided by m minus n factorial when x is equals to 0. Therefore, using Taylor's theorem, we get the following identity. Theorem 4.15. Let m be any real number. Then 1 plus x to the m is equals to the summations of m choose n times x to the n, summing for all n which is greater than or equals to 0, where the sum is taken over all non-negative integers n. Thus, 1 plus x to the m is an infinite power series if m is not a positive integer. Note that if m is a positive integer, then m choose n is equals to 0 if n is greater than m. And therefore, we only get a sum of m plus 1 elements for 1 plus x to the m. Example 4.16. Find the power series expansion of the square root of 1 minus 4x. Solution. By Theorem 4.15, the square root of 1 minus 4x is equals to 1 minus 4x to the 1/2, which is equals to the summations of 1/2 choose n times minus 4x to the n, and we summing for all n which is greater than or equals to 0 for such a term. To simplify this expression, we have to find a simpler form for 1/2 choose n. 1/2 choose n is equals to 1/2 times minus 1/2 times minus 3/2, 3/2, and so on times minus 2n plus 3 divided by 2, then divided by n factorial. If we taken out all those minus factors, that will be equals to minus 1 to the n minus 1 times 2n minus 3 semi-factorial divided by 2n times n factorial, where 2n minus 3 factorial stands for the product of all odd integers from 1 to 2n minus 3 and is called 2n minus 3 semi-factorial. Substituting this to formula 4.12, we get the square root of 1 minus 4x is equals to the summations of 2 to the n times 2n minus 3 semi-factorial times x to the n divided by n factorial, summing for all n which is greater than or equals to 0. Multiplying both the numerator and the denominator of 2 to the n times 2n minus 3 semi-factorial divided by n factorial. If we multiply both the numerators and the denominator by n factorial, we see that 2 to the n times 2n minus 3 semi-factorial divided by n factorial is equals to 2 times 2n minus 2 factorial divided by n factorial times n minus 1 factorial, and therefore the square root of 1 minus 4x is equals to minus 2 times the summations of 2n minus 2 choose n minus 1 times x to the n divided by n, summing for all n which is greater than or equals to 0. Notes: exercise 19 and 20 concern two interesting areas of combinatorics. One of them is unimodality and log concavity, and the other is the combinatorics of lattice paths. Interested readers can consult Chapter 8 for an introductory text on the topic. Another good starting point is where lattice paths are used to prove unimodality results in a very accessible way. After that, we recommend for unimodality and log concavity results from the reference 12 and the reference 21 for lattice path enumeration.